This is Earth Science Lecture number 5, Mineral Families and Resources. In this lecture, we're going to look at how minerals are grouped together and understanding resources on Earth. We'll look at how minerals relate to the common elements we find in Earth's crust and the major mineral families and what their economic uses are. Minerals, we know, and if you've ever seen a mineral guide, you'll see that there's like 4,000 minerals listed. There's 4,000 minerals known in nature. But most of these minerals are actually rare. There's a smaller group which we call rock forming, and these minerals are much more common. These minerals are actually those which we find in most rocks, and those are the ones that you'll be identifying in the lab. Looking at the periodic table for a moment, most of the common elements that we have in minerals, if you look pretty much up to element 26 iron, everything under that on the periodic table is typically an element that we commonly find inside of a particular mineral. And so let's look at the most common elements that we have in Earth's crust. The most common elements, oxygen being the greatest, and if you look at this graphic here, you could see that almost half of all of the elements in the crust are oxygen. Silicon is about a little bit over a quarter, about 27%. Then we have aluminum, iron, calcium, sodium, potassium, and magnesium. So these are the individual elements. Obviously, the elements aren't just floating around by themselves. They are found within minerals. But these are the most common elements that we have in the minerals of Earth's crust. And since silicon and oxygen make up the most elements in the crust, it's not surprising that we have a whole family of minerals named after them. These minerals are called silicates. A silicate mineral is a mineral that contains the elements silicon and oxygen. Actually, most rocks contain silicate minerals, and so these are most of the rock-forming minerals. Now, how do silicate minerals form? Well, silicon and oxygen come together in a structure which is called a silicon-oxygen tetrahedron. A tetrahedron is a pyramid-shaped structure which is composed of 4 oxygen atoms. And notice the oxygen is significantly larger than the silicon atom. The 4 oxygen atoms come together, sit very nicely, touching each other, and there's just a tiny little space in the middle where silicon can rest. This is an expanded view of this compacted structure. So a silicon-oxygen tetrahedron is 1 silicon atom and 4 oxygen atoms. You could write its chemical formula as SiO4. And these tetrahedron are the building blocks of the silicate minerals. I like to think of Legos. These kind of make the Legos, and you put them together in various ways, and you can construct all of the different silicate minerals. Please don't memorize these different structures, the names of the structures, but I'd just like to show you how these tetrahedron can connect together to make the silicates. A single tetrahedron makes the mineral olivine. A ring of tetrahedron can come together to make the mineral beryl, which is another word for emerald. You could actually make a chain of tetrahedron, which form the pyroxene minerals. 2 chains together, which form the amphiboles. You could have sheets of the silicon-oxygen tetrahedron connected together, and these form the mica minerals. And then other more complicated structures can form to create the feldspar and quartz minerals. And so here are the common silicate minerals, and these are ones that you're definitely going to be looking at in lab. My question to you is, are these silicates? And how do you know? Well, if you recall, a silicate mineral is one that contains silicon and oxygen. If you look at every single formula here, you could see Si and O, which tells us that the mineral contains silicon and oxygen, so therefore it is a silicate mineral. Now there's one more degree of complexity, and that is silicate minerals are divided up into 2 groups. The first group is called ferromagnesian. A ferromagnesian silicate mineral is one that in addition to silicon and oxygen, also contains either iron or magnesium. And iron has the chemical symbol Fe, and magnesium has the chemical symbol Mg. The other group of silicate minerals are called non-ferromagnesians. Non-ferromagnesians do not contain iron and magnesium. They typically contain some other element, such as potassium, sodium, and perhaps some calcium. So if I go back to this previous list, let's see if we can figure out which ones in the list are ferromagnesians and which are not. Would olivine be a ferromagnesian silicate? If you answered yes, you are correct because it has the Mg and the Fe. It is considered to be a ferromagnesian. I'll kind of write an F there for reference. What about pyroxene? Pyroxene is also a ferromagnesian. What about amphibole? Looking through the complicated chemical formula, you see Fe and Mg, so this is also a ferromagnesian. What about biotite? Yes, it has Mg and Fe in it. Muscovite? I don't see it. So this would be a non-ferromagnesian. Potassium feldspar is a non-ferromagnesian, and quartz is also a non-ferromagnesian. Now, ferromagnesians and non-ferromagnesians can be distinguished by one another. So the ferromagnesian silicate minerals are olivine, pyroxene, amphibole, and biotite. And these minerals are typically dark in color, like you see in the picture. Olivine is this green color, and green in earth science is considered to be dark. We have black augite, black hornblende, and biotite, which is also black and can be brown sometimes if you have a thin sheet. The non-ferromagnesian silicates are minerals such as quartz, potassium feldspar, and muscovite. These are typically light in color. They'll either be clear, pink, or a whitish color. And so when we get to our lecture on this topic, we're going to examine how minerals are grouped into families, and other minerals will be grouped into various families. So we'll see a little bit more about how this is done. So to look at the other predominant mineral groups that exist, you're not responsible for memorizing these, but just to show you what they are. There's a group called carbonates. This one includes the mineral calcite. Remember, that's the one that fizzes. It's a very common mineral in sedimentary rocks. There's the mineral group called oxides. Hematite and magnetite, that's the one that attracts a magnet. Hematite is an ore of iron. These two are oxides because they contain oxygen. Sulfides, these are mineral groups which contain sulfur. Galena and pyrite here's a picture of galena down here, are those. Sulfates, they contain sulfur, but in a compound, sulfur dioxide, so SO2, and that forms this mineral called gypsum. They're also referred to as salts. They actually do have a salty appearance. Native elements, actually, minerals can be composed of just one element, and that's what the native elements are. So either you could have just carbon and make diamond, you could also have just carbon and make graphite, you could have just copper, just sulfur to make those native elements. The last mineral group is called halides, and these typically contain what are called the halogen elements. And to show you what the halogen elements are, I'm going to go back to the periodic table. There's a group on the periodic table called the halogen group. Fluorine, chlorine, bromine, iodine are part of this. So if a mineral contains any of these elements, it's put into that halide group. And one of the things that you're going to be doing for your lab is on this next slide. I'm sorry, I clicked way too many times, so just going to go back for a second. I have to have some patience here, I think. Economic uses. And so one of the big reasons why people study minerals is because a lot of them have economic uses. You'll see lots of these are called ores, which we'll define in just a moment. Copper, mercury, iron ores. Some are used for salt. Some are used for fertilizer, for jewelry, for plaster, and so on. So this is what you should refer to when you're doing your minerals lab. There's a last column of the mineral table, which is the economic use, and so you can find the answers to those questions here. Now, mineral resources, we did see on the previous slide the term ore. What does ore mean? An ore is basically a deposit that you could get one or more minerals that you can extract it in a profitable fashion. And so if you take into account the cost of the mining operation, which is very expensive, if there's enough of that particular mineral there to be profitable, then you have an ore reserve. Now, there's some issues associated with mineral resources. One big thing is that, if you recall from our first lecture, we described what it meant to be non-renewable resource. A non-renewable resource is one that's essentially present on the earth in a finite amount. It takes millions of years for these resources to form, and so when we use them, we should consider that as we use them, we essentially use them up. There's an uneven distribution of mineral resources. It's often related to plate tectonics and past geological environments on the Earth. And most of the industrialized nations on the globe have used up all of their mineral resources. And so we find that there's a lot more development in the less developed countries. They're now finding new sources there. Will we run out? Well, it is possible to find new sites for mineral resources, but we do think, since they are non-renewable resources, there could be shortages in the future, and shortages which would be important to consider going forward. This is one of the reasons why recycling is so important, because a lot of these resources are in such a finite amount. Here's just a map of the world showing which countries and which locations have particular mineral resources. You could refer to this in your textbook. And just a little aside on how different mineral deposits are formed. A lot of people that work for mining companies would study past tectonic environments, because a lot of it has to do with the geological conditions that were experienced at a location in the past, because we see that it's the geology that controls how different mineral deposits can develop. There's first listed here a hydrothermal environment, and this is where you have basically volcanically heated water. And in water in general, there's just a trace amount of precious metals and minerals within it. And the process of the stuff that's dissolved in the water coming out of solution, what we call precipitating, it makes it become concentrated, and you could actually form a deposit. So where you have volcanically heated water erupting, you can often get interesting mineral deposits developing. We'll see in an environment which is called a metamorphic environment. This is where you have lots of heat, lots of pressure, and something called pore fluids. Again, it's that water that goes through the rock that concentrates those various minerals. And so in those environments, you could tend to find interesting things. In a magmatic environment, what this implies is that it was part of what's called a magma chamber. Magma is melted rock. And so within a magma chamber in volcanically active areas, certain minerals will form within that liquid melted rock. And these minerals that form are those that can form at very high temperatures. When the mineral crystallizes, they typically become denser, and they fall down to the bottom of the magma chamber, and they can accumulate and become concentrated. The last environment that we look at, a sedimentary environment. This is an environment where you have a lot of evaporation. So if you had a sea that had lots of stuff dissolved in it, the water was dissolved in the lake, and slowly the water evaporated away. The stuff dissolved in the water, the salts remain behind, and you could get a mineral deposit of salt forming in that fashion. Placer environments are interesting because these are actually where we get a lot of our gold and precious metals. These are always transported from their original site by water. And essentially, as the water moves along, the metal can tend to concentrate in places where the water slowed down. And so understanding that process of flowing water and where you would have faster moving water and slower moving water is very helpful. The metals also tend to be quite dense, and so they can fall down and accumulate together because of their heavier nature. And the last type of mineral deposit is called a residual deposit. And this is also in a sedimentary environment. If you have a lot of chemical weathering of, let's say, a metal, the metal can transform and rust. And the rusting process produces a new mineral. That's actually where a lot of iron comes from through that rusting process. So we'll be looking at this in class when we talk about mineral families and resources.